All right. We've already covered epoxides a little bit in Chapter 9 when we were talking about anti-diol formation. And we said that if you have an alkene, something like this, you can react it with a special reagent to form an epoxide. What reagent is this called? Peroxy acid, if that's a hint. I heard it. MCPBA. So the question is, what does MCPBA stand for? Stands for alphabet soup?
Metachloroperoxybenzoic acid.
Oh yeah, there we go. Metachloroperoxybenzoic acid. So we've got a chlorine coming off of a benzene, and then we've got this functional group off to the right that is a peroxybenzoic acid. It's not a normal carboxylic acid because it's got the two oxygens. So it's in between a peroxide and a carboxylic acid. The other one that you often saw on sapling is peroxyacetic acid. Both of these can be used to form epoxides. Chloroperoxy.
We don't have charge on the oxygen.
Benzoic acid. On which oxygen? Nope. Because we still have two lone pairs on there, right? So if we try to do the formal charge for oxygen, it's a neutral oxygen in this case. And then this one is peroxyacetic acid. Both of these reagents are commonly used. If you go on and take advanced organic chemistry, you'll cover quite a few more. However, the key feature in all of these is this peroxy bond. You're going to donate one of these oxygens to the double bond on the epoxide. I'm not overly concerned with the mechanism. You can pull it up in your book. I just want you to remember that MCPBA can be used to form epoxides from alkenes. The second reaction that popped up on sapling inadvertently was the halohydrin reaction. And this can also be used to form epoxides. So if you remember with the halohydrin reaction, we've got bromine and then what else? And water. When this happens, we get a bromine added across our double bond. And I'll just put this bromine as a wedge. And then you also get an alcohol along with the enantiomer. It's important to remember that this is anti-addition, and it goes through a bromonium ion intermediate. So the alcohol will normally be attached to the more or less substituted side. More substituted side. In this case, it doesn't really matter. You can put it on either side because neither side is more substituted. After you've made your product, you can treat it with sodium hydride. And what do you think will happen if you have sodium hydride around? Yeah, it'll just deprotonate your alcohol. Oops. So it can deprotonate your alcohol. It can give you an alkoxide, which is your oxygen with your negative charge. You now have a bromine over here. All right. And then what do you think could happen next to form an epoxide? We can do a sneaky backside attack on that bromine and kick it off. So this is similar to an SN2 reaction, or it is an SN2 reaction. It's just intramolecular SN2. And when you do this, you end up forming a new epoxide. So either method can be used to form epoxides. However, I will say that the MCPBA route is far and away the most common method. What's the problem with the halohydrin reaction if you've got things like a carboxylic acid on there?
Deprotonate.
Yeah, exactly. A strong base will deprotonate any other acidic sites on your molecules. So this is really only effective for relatively simple molecules that don't have any other acidic sites on them besides that alcohol. MCPBA is a lot more forgiving with other functional groups. All right, so let's do a practice one. just for review. And I'm going to do an isopropyl group here. We're going to react this with MCPBA. And I want you to give me the product or products of this reaction. With the correct stereochemistry, too. I'll give you guys a hint to get you started. We're going to make an epoxide. Pretty helpful, huh? And we're going to make 2 epoxides. 2 different epoxides. All right, let's go over this really quick. The main thing to look at with your alkene is to identify the groups that are cis to one another, right? So we'll just call these cis, in quotes. They're not really cis because they're not identical groups, but they're on the same side of the double bond. That means when you go to draw your epoxide, this isopropyl group should be on the same side of the ring as that methyl group. Same thing over here. We've got this methyl group that's cis with that other ethyl group. That means in the back, we've got a methyl group, and then over here, we've got an ethyl group. Same thing with this one. Over here, you would have this isopropyl group as a wedge, this methyl group as a wedge, this ethyl group as a dash, and this methyl group as a dash.
Why not just try an enantiomer?
Well, are these enantiomers? Let's just stop and double check. Are there mirror images? Let's use the power of computers. Are they mirror images? Yeah, they're mirror images of one another. However, if you try to rotate it and overlay them, they are non-superimposable mirror images. What does that mean they are? Enantiomers. Diastereomers are non-mirror images. So in this case, we end up with the mixture of enantiomers out of this reaction. So you always have to double check your stereochemistry, and you can't neglect the fact that you oftentimes form enantiomeric pairs. Always double check your stereochemistry. It's quite often that I see students just draw straight lines without dashes and wedges on epoxides. You have to indicate the stereochemistry on those carbons because they are stereocenters. There was a big problem for a long time because anytime you did an epoxide reaction, you would always get a mixture of enantiomers. However, in the 90s and late 80s, there was actually a route developed where you can form one enantiomer over the other. So I wanted to briefly present this. Enantioselective Epoxidation. This won the 2001 Nobel Prize. It went to Barry Sharpless, William Knowles, and Ryoji Niori from Japan. And they found that if you had a specific type of alkene where the alcohol was in the allylic position, so allylic alcohol, you could selectively react one face of your alkene. Oh, shoot, that's not working. The way they did this was they used a special reagent where we have a peroxy I'm trying to remember how to say this. Peroxy. I'm going to have to look that up. I forgot. But we have that same oxygen-oxygen single bond in there. I'm going to have to edit the online video. And then the catalyst that we use is a titanium catalyst. So it's OCH, CH3, 2. And then we've got 4 of these ligands coming off of there. And then they threw in this chiral component, which was diethyl tartrate. And when they did this, they got exclusively one enantiomer, or at least they got one enantiomer in a huge excess over the other. If they did the same reaction using this peroxide and same catalyst, but this time they used the negative diethyl tartrate, meaning it rotates light in the opposite direction, then we would get the opposite epoxide. And again, you may be saying, why does this matter, Jeff? This is silly. One epoxide's just flipped upside down. Why do you guys think it matters? Drugs, right? We went over this first term. We said oftentimes if you have the incorrect enantiomer of a drug, it can be super duper toxic. For a long time, they worked around that by knowing that they were going to have to discard half of their product that was the wrong enantiomer, and they just knew that. This route not only enabled them to make it enantiopure, but it raised their yields of their desired product considerably, which is why they got the Nobel Prize for this. So let's take a look at the catalyst system, just because I think it's interesting. Oop.
How do they find out this way to anti-selective?
They are much, much smarter than most people on this planet, and they have a huge amount of experience. Oftentimes it just comes down to working really hard, trying a ton of different catalyst systems.
So they just randomly pick a catalyst and say, well, this one probably will work, and they just try it?
Yeah, oftentimes when you're developing a catalyst, you don't have a catalyst in mind. You're just trying out a bunch of different catalysts, and that's probably what they did in this case. The really innovative part was using this diethyl tartrate, which is a really cheap, commercially available, but chiral product. So we'll write OET, and this one's positive diethyl tartrate, so I'll write DET. This one's negative diethyl tartrate, and this one has the alcohol sticking back. When you mix these together, you form a chiral catalyst. So we'll write one of these. So you can pick one. When you mix these together, you form a chiral catalyst that will only react with one side of your alkene. The reason that I'm showing you guys this is, like I was saying before, oftentimes the Klein textbook shows traditional old school chemistry. This is how people nowadays tend to do epoxidation reactions. This is really gentle, it's very enantiospecific, and you can control it to a very, very high degree. So I just wanted to show you guys one of the more modern reactions rather than just throwing MCPBA and getting a mixture of enantiomers out.
I'm sorry, you sound like an advertising spokesman.
I know. All right, Monday when we come back, we'll talk about ring opening epoxides with a variety of different nucleophiles under acidic and basic conditions. All right, have a good weekend.